having me. I was looking forward to visit you in person. It's been a really long since I visited the Hebrew University last time, but maybe we'll have another options in the futures. Anyway, so what I'm going to talk today is a little bit about what I've been doing in my lab. I'm in the Weizmann Institute for the last, I don't know, maybe 1 or 2 years. Maybe not surprisingly, it's kind of revolved around this deep learning issue, but we have a rather kind of a specific aspect on this huge machinery, which is how to adapt it to regular and geometric data. So just before I start, I want to, something is stuck here, sorry. I want to show just a quick image of the team. And there are some people who collaborated on the work of the different works I'm going to show are not in this image, so, but I'm going to give credit anyhow. The first part is mostly in the PhD thesis of Chagai Maron here in the bottom left, and the implicit stuff I'm going to show is mainly done by Matan Atzmon, Amos, and Lior. Okay, so to set up the stage a little bit, I'm going to talk about like two minutes about what is the kind of data I'm considering as input, or and in general, we can think about like this hierarchy of data structures starting from sets, where a set can be imagined just as an unordered collection of items. In our case, each item is going to be a feature vector, and in this talk, all the feature vectors will be represented as colored spheres or boxes. So anyway, colors represent feature vectors. The next step in this hierarchy is where we have not only information on specific elements, but also we have maybe information on pairs of elements. So for example, graphs. Graph would be attaching a 0 or 1 to pairs of nodes, but you can also attach also other feature vectors, whatever you want. And in the highest point of this hierarchy that we want to consider would be hypergraphs, where we attach some feature vectors or colors to any tuples of nodes. So in this case, we have triplets and pairs and so on. So this is these are basically the type of data that we will call irregular data in this talk. And to instantiate things a little bit, we can think about these feature vectors or these colors indicating, for example, 3-dimensional coordinates in some world coordinate system. So for example, if you take a set and for each element in the set you prescribe an XYZ coordinate, you would get a creature that some people refer to as a point cloud, like shown here on the left. If you do the same process for a graph, you would get a 3-dimensional structure, but you also have some relation between nodes. You can think about this as a way to model things like molecules, for example. And for hypergraphs, it's a kind of a vast generalization, and you can do many crazy things with it. One thing is if you want, for example, to model shapes, you can use hypergraphs of order 3, so you can encode nodes, edges, and triangles, and think of these as a way to represent or approximate a 3-dimensional surface. So on the right here, it looks like a smooth surface, but it's actually a hypergraph. It's or more specifically a triangular mesh. So it has a 3-dimensional coordinate attached to vertices, and there's edges and triplets of vertices connected to form small triangles that kind of describe this shape. And now the goal of this talk, or things we are doing now in the lab, is to try to find how to adapt neural networks to deal with irregular and geometric data of the types I've just mentioned. And what I'm going to cover in this talk are two pretty different approaches to this problem. The first is more like an algebraic approach, where we kind of think about symmetry of these structures, and using the symmetry, we come up with a neural network which are well defined on this data and are good for generalizations and approximations. And in the second part, I'm going to talk about a way to represent geometric data as zero-level sets of neural networks. So it's going to be implicit representation where the implicit function is a neural network. But I'm going to start, so the first part of my talk is going to be about using symmetry and equivariance to define neural networks on irregular structures, in particular graphs. Graphs will be kind of the main issue. By the way, I have some noise here on the background. If it bothers you, let me know. I'll close the window because I'm not sure how well it's kind of capturing this microphone. So let me know if you don't hear me well, or this screaming of the kids outside make you anxious. Okay, so the first thing we want to do is think about symmetry and equivariance. I'm going to define everything precisely, but the first thing I want to do before we actually go into building something, we would like to first kind of agree between ourselves, how do we represent irregular data like sets, graphs, or hypergraphs as a data structure in a computer. Now, I'm not going to think about anything like computational complexity at this point. I'm just going to do it so it will be at least mentally easy to think about these things. So the way we're going to do it is, for example, if we start from the left-hand side of the slide, so we have a set which is a bucket of elements, a bucket of colors, or a bucket of numbers if you want. We're going to represent it as a vector of the same length. So if you have 6 elements in the set, we're going to represent this set as a vector in R6. If we have a graph with 6 nodes, we're going to represent it as a matrix of 6 by 6, where on the diagonal, we're going to plug in the colors or the values on the nodes. And off diagonal, we represent values that are attached to edges. So for example, I don't know, the value here, I called everything gray, but the value here is basically going to be maybe the value that either 1 or 0 if we're just encoding an adjacency of a graph, or some value encoded with this edge. I see things on chat. I'm not sure. Do you want me to answer questions?
I actually just said that maybe it might be better to close the window because sometimes we do hear the noise. So if it's possible.
Oh, okay, sure. So I'll do that.
Thank you.
Okay. Anyway, so I was saying that, for example, at this entry would represent the information attached to this edge. So there's also possible to do non-symmetric graphs and so on. So anyway, you can think about putting the adjacency outside the diagonal. In diagonal, you can put things attached to vertices. And when you go 1 dimension higher or several dimension higher, you can think about representing a hypergraph with maximal hyper edge of size, let's say 3, as the 3-dimensional tensors, and each tuple, 3 tuple of vertices would have its own place in this tensor to represent the information attached to this tuple. Okay. So once we represent this, these data structures as vectors or tensors, we did something. We made a choice, and the choice we made is we picked up a specific order of the elements. So we put the yellow, for example, first, and the pink we put it third. But obviously, if we want to represent a set, this order has no meaning. So what we're going to do is we have to take or think about the different symmetries of this representation, or the different ways in which different vectors are going to represent the same set. So in order to do that, we're going to think about an action of the permutation group on these vectors. So for example, if you think about a vector in Rn, we have the permutation group Sn, which shuffles entries in this vector. So for example, if we think about this permutation, which this notation means that the first element is going to move to the third to the first, and everything else is going to be left at place. Then if we apply it to this vector, to x, we denote it by dot. So sigma dot of x would basically will switch the yellow and pink and leave everything else in place. Now, what we want to say is that all the different permuted version of x represent the exact same set. So this is, you can think about an equivalence relation that is defined as the orbit of this action on the vector. So we made a choice by representing a set as an ordered vector, as a tuple, but we keep in mind that all the possible ways we could order it would represent the exact same set. And in a second, you'll see how this comes into play when we are actually constructing neural networks. Now, of course, we can continue this game not only with sets, we can think about graphs, which are represented as matrices in our case. So how does this action of permutation acts on graphs? So you can imagine that in graphs, when we come to encode it as a matrix, we also made a choice. We numbered the vertices of the graph. So had we ordered the vertices of the graph in a different way, the matrix that represent the graph would go under a transformation where the rows and the columns would be permuted by the same permutation, which is exactly the permutation we used to reorder the vertices. So again, if you use the same permutation as before, the one that switches the first and third element, then the action of this permutation on this matrix would mean to switch the first and third rows and the first and third columns. So the output would be this, meaning that this sigma of x, this permuted matrix and the original matrix represent the exact same graph. Okay, that's exactly in graph, like in graph isomorphism, where we look for this permutation that would give us the same matrix. Okay, and of course, the same rule holds also for high order tensors. Now, when we advance one step further, and now what we want to do is we want to think about functions between symmetric objects. So I call these sets or graphs or hypergraphs symmetric objects. And basically our goal is to learn some sort of a function between symmetric objects. For example, if you think about the first function here is a function between set and set. For example, just to make things concrete, maybe the function that try to find where is the yellow element in this set. So it returns a probability vector where you put the probability 1 on the yellow or close to 1 and small probability values outside this first entry. You can also think about functions that you want to approximate, which are functions on graphs. Okay, for example, find the connection between the yellow and the blue elements or whatever. I don't know, count the number of connected components and put it on the diagonal. Whatever kind of function you want to find between graphs, classification of nodes, classification of edges, what have you, whatever function you have in mind. And there's also functions that can go between symmetric objects. For example, between a set and a graph. For example, enter a set and learn connections between nodes. So you learn a graph structure from nodes, or maybe even from a graph to a single number. Single number is also a tensor. I will mention it in a second. Just like one number which represents number of connected components on the graph, whatever. So anyway, there are functions between the symmetric object that we want to approximate. But there is an important question here, which kind of stems from the previous slides, which basically is we want to think about function between the symmetric objects, but we represent it as function between the vectors or the tensors, which are ordered creatures. So what exactly do we need to request from f to satisfy? What are the properties of f that would guarantee that although this function works between vectors, for example, or matrices, it actually is well defined between the symmetric object, between sets and graphs. So one way which is very natural to do it is to think about equivariance. So what I want to claim or convince you with this slide is there is a property which is called equivariance. And once f holds this property, satisfy equivariance. So once f is equivariant, then f is well defined as a function between symmetric objects. For example, between sets, if I have f between vectors in Rn, which is equivariant, then it well defines a function between sets of n elements. Okay, so let me try to convince you. So what is equivariant? Equivariant says the following. Let's say, think about this function on sets that identifies the yellow object, for example. And now you have a function that maybe tries to find the yellow element in the vector. So we call this an f. And you have a permutation, which is exactly the permutation I introduced before, that's switching the first and third elements. But this is for any permutation. And now what you ask from F is that applying the function and then the permutation will lead to the same result as applying the permutation and then the function. Okay, so we ask that this diagram is commutative, and this is equivariance. Mathematically, it basically means that F and the action of the permutation commutes. Okay, you can see that what does it mean? It means that if you take an X and you entered your function a permuted version of X, which we know is in the same equivalence class as the original X, it represents the same set, same vector, same hypergraph, whatever, what have you, then the output would also be in the same equivalence class, whether it's a set, a graph, hypergraph, or whatever. So this is a sufficient condition, if you want, for this function F to be well defined between symmetric objects, between sets and hypergraph, hypergraph and sets, whatever you want. So this is on one hand a sufficient condition for well-definedness of symmetric object, but it actually carries much more power than that, because it also provides, later we'll see, it will also provide a lot of expressiveness when incorporating models. But anyway, this is just a mathematical definition that is a sufficient condition for F to be well defined as a function between sets. So if you make a different choice of a vector that represent the same set, you are guaranteed that your output would be a different representation maybe, but of the same set or graph or whatever the output domain is. So I hope this notion is clear. Let me just show it, for example. I wanted to write, I want to say that this is kind of a really general property. So we can think about equivariance between arbitrary tensors. So sets and graph are two examples, but you can think about on any tensor you want. So if you have a k-order tensor and l-order tensors, meaning this one attaches number to k tuples of vertices, and this one attaches information to l tuples of vertices, then we can ask that F would be equivariant. The only thing to note here is that this dot here, so this sigma acts on the k indices of x, and this sigma acts on the L indices of f of x, okay? So I define the action of sigma regardless of how many n dimensions we have in the tensor. So if this is, for example, a matrix, this acts on both rows and columns, and if this is a set, then this acts only on the rows. Okay, so equivariance can be defined between all tensors. For example, maybe just one more slide. This is like an image that shows exactly the same thing for graphs. So a function between graphs, which is a function between matrices, is well defined as a function between graphs if F commutes with the action of permutation on rows and columns. Okay, so I think I spent enough time on this equivariance idea. I want to mention that equivariance is also, it's kind of a generalization of invariance. So you can think about a tensor, you have a set, you have a graph, but you have something even smaller in a sense than a set, which is just an element which has no relation to the number of elements in the set, okay? So there's no n to the power here. In this case, equivariance would mean that sigma acts on all the dimensions of n in the tensor, but there's none. So the only representation of sigma would be the identity. So all I'm saying is that if you think about equivariance, when you have a function from, let's say, a vector to a number or a matrix to a number, just a scalar number, then equivariance would mean that this function is invariant. Invariant meaning that it will spit out the same result regardless of what representation of your symmetric object is inserted as input. Okay, and now we are basically in the first slide that is related to neural networks. And what we're going to do is we're going to construct neural networks based on equivariance principles. So we want to construct neural networks that are well-defined on sets, or are well-defined on graphs, or are well-defined on hypergraphs. Okay, so we saw that a sufficient condition is that these neural networks would be equivariant. So how do we construct equivariant neural network? So we have a pretty simple way to do it. So the first thing that we consider is maybe the most basic neural network possible, which is the multi-layer perceptron. So in my drawing, these gray blocks will always indicate variables. So in the input, it's the input variable, and this is the output, and the inside is like a hidden variables. And arrows represent the layers, the transformations. So in multi-layer perceptron, every arrow is basically a composition of two things: an affine transformation, A, and entry-wise nonlinearity rho. So for example, ReLU. Now, one thing that is good for us is that whenever you do an entry-wise function, linear, not linear, doesn't matter. It's a equivariant operation by construction. Okay, this is a small exercise. If you take every entry in a vector and apply ReLU, then this operation is equivariant. You can, if you enter a permuted version and then do ReLU, it's like do ReLU and then permute it, right? You can think about it a little bit in your head and convince yourself that's the case. So we're already in luck that we don't need to care about the nonlinear activation of neural networks. These will be permutation equivariant for free. However, general affine transformation are not equivariant in general, okay? So the general tactics would be, okay, so in order to create an equivariant network, let's restrict the affine transformation to be equivariant, okay? So there's a mathematical question. What is the collection of all equivariant affine transformation between tensors? Okay, once we answer this question, we can construct, hopefully, this type of networks, and these networks is going to be equivariant. If we want an invariant network, so for example, if you want to learn function that provide maybe a number per graph that represents something about the graph, then we might want to add an invariant layer. After a single invariant layer, everything else is going to be invariant. There's no point in putting more than one invariant layer. So here we have a fully connected end to this network, and this whole thing is going to be invariant. So the gray part is going to be equivariant. It's going to learn a value per node or per vertex of the set of the graph, and the entire thing is going to be invariant. It's going to produce a number or a vector which is invariant to the specific way that X is represented at the input. Let us provide a small, short, like a proof that this is indeed the case. So mark all the hidden variables by X with a subscript I, and the input is X. And now imagine that you put into this network, instead of X, you put sigma of X. So the first thing that you apply is an affine transformation, but this affine transformation is equivariant. Again, I didn't prove that there exists any of those, but assuming that there are, and we only use those, then sigma would commute with those. Then we have a nonlinearity, right? So also nonlinearity, we said if it's entry-wise, then it's also equivariant. So sigma going to commute also with this. And then by induction, we can basically see that sigma is going to basically commute with all the interior variables until the end. Now, if we stop here, we get equivariance. But if we have an invariant layer, then we can also see that the output from the yellow part onwards is invariant. So the only thing I said here is that equivariance is something that sustains compositional function. If I compose invariant function, if I compose equivariant functions, then I get the equivariant function. So the fact that I use affine equivariant transformation, nonlinearity is equivariant by construction, and equivariant is something that is closed under composition, I can construct neural networks which are versions of MLPs which are equivariant or invariant. Okay, so now this is a good point to kind of say what have people have done in this landscape, and maybe I will kind of concentrate on our contributions in this domain. So first of all, maybe the world's most famous example of equivariant network are convolutional neural networks. So if you think about a transformation group, which is not permutation as I mentioned them, but rather translation. So you think about an image, just to make things kind of mathematically clean, think about a flat torus, so like a periodic image, and you have translations. So this is a group of transformation. It also does something to the input, and we can think that all these translations basically represent the same object, the same image. And now if you think about all the linear transformation which are equivariant to this transformation, then you would get the set of convolutions. And now if you restrict your MLP, you restrict the linear part to be only convolutions, you're going to get an equivariant translation networks. I know there's the pooling, and all that stuff, I'm leaving that out. I'm talking about fully convolutional neural network without pooling. Then what you're going to get is convolutional neural networks, and this is basically a great success of equivariant networks. Maybe the biggest success till date. What about other groups? So translation is good. So many researchers have kind of thought about more elaborate transformation than translation. Some added 90-degree rotation. Some thought about continuous rotations, SO3, rotations on the sphere, scaling. So there's a lot of work in that domain. However, if you want to think about, again, graphs or sets in the context that I mentioned, you have to deal with the specific transformation that I've described. And in this world, there are also some works have been done. So the first one that at least we were able to find is like 25 years ago, where people have considered arbitrary permutation groups. The problem with arbitrary permutation groups is that it's a huge space. Basically, any finite group can be seen as some subgroup of permutation group. So as you can expect, this is more like a theoretical paper. There are no closed form or actual formulas, and there's no construction of concrete networks. 2 years ago, people have started to work with more concrete setting, and I think one of the most seminal papers in this field is deep sets by Zahir et al., which actually considered the case of sets to sets, like I mentioned before, and they were able to characterize the affine equivariant transformation, all of them. There are very few. It's basically just the identity and summing and the sum. And basically, they kind of were the first point where people were started to look into this equivariant stuff. There were some generalizations to tables, which is a kind of interesting data structure, but I didn't mention it. But the very interesting problem of graphs, so how to construct equivariant graph networks, was not known. At least we couldn't find any closed form formulas for the equivariant linear transformation, and there was no any kind of characterization of all the possible linear layers that are equivalent to graphs. So that's the first thing, and there are no, at least we were not aware of any results with going between different irregular structure, like sets to graph, graph to sets, hypergraphs, and so on. So the first contribution I would like to present is basically characterizing all the linear transformations between arbitrary tensors, including the new and important case of graphs. So if you think about equivariant layers between k-order tensors and l-order tensors, if you take k and l equal 2, then you basically characterize all the linear transformation which are equivariant between graphs. So you will be able to construct graph neural networks this way. Okay. So let me describe this result. So basically, this result provides the dimension of the space of equivariant linear operators and provide orthogonal basis that is really easy to implement as the affine part of the MLP. Just to kind of give you a taste of what is the number of these operators. So if you think about the case where you want to think about linear equivariant mappings between graphs, then k and l equal 2, this theorem says that the space of equivariant linear transformation between matrices will be of dimension Bell k of k plus n. So Bell is the Bell number. It's a combinatorial number. And I'm gonna define it, define it by example here. So Bell number of 4, which is the number of independent linear transformations between matrices, is the number of ways. So Bell number of 4 is the number of ways you can decompose a set with 4 elements to subsets. Okay, it's a combinatorial number. So for example, Bell number of 4 is 15 because there are exactly 15 ways you can decompose a set with 4 elements to subsets. Here are examples. For example, one thing that you can do, you can put every element in the set in its own set. That's one option. You can take these 2 elements and put it in one set, and each of these elements in their own set. That's another option. Here's another option. Here is the option of putting all of them in one set. So if you enumerate in your head all the possible ways, you'll see there are exactly 15 options. So there is like this magical number of 15, which is exactly the number of ways you can map a graph to a graph in a way which is equivariant, in a way which is well defined. So you can map a matrix to a matrix in a way which will be well defined for graphs. Okay, so the big thing about this theorem, or the important thing to note, is that this dimension is completely independent of n. So it means n is the number of vertices in the graph, if you want. Okay, so regardless if you have a 1 billion vertex graph or a graph with 12 nodes, 12 vertices, you're always going to have 15 degrees of freedom to define a transformation between the graphs. So this already kind of gives the hope that this will be good for generalization, right? Because you can learn on small graphs and you can apply it to large graphs. It's always the same parameters that define those transformations. So here's equivariant networks specifically for graphs. So we have those. So each of these, the input is going to be something of dimension n times d. D is the feature dimension. We're going to ignore that. So the input is going to be, for example, the adjacency matrix, which is n by n. And then each layer here, which is a black arrow, is going to have 15 degrees of freedom. That's the Bell number of 4. And as usual, if you have a feature dimension, you're going to always have the number of degrees of freedom will be times d in times d out. Okay, that's because there's no symmetry in that dimension. Nothing is decreased. All the possible in transformations in the feature space are available. So each of these, so these networks going to have 15 times d in times d out. Okay, that's what happened. And now, so this is a well-defined creature. And we can encode it, we can run it, and immediately there are several questions that comes into mind about this model. The first question is how this model relates to popular or existing graph neural networks. Maybe the most popular graph neural networks is message passing. So how is that related to message passing? So we came up with a model from really basic principles, but it's not clear whether it is expressive or powerful. So what I'm going to show you is actually this model is at least as powerful as message passing. It was recently proved that it's actually not more expressive. However, it turns out that if you increase the tensor order of the hidden variable, you can actually increase its expressiveness and you can go beyond message passing. And in fact, if you increase the tensor order without a bound or with actually an exponential bound, you can get a universal graph model, which is practically not useful, but theoretically, there are not many equivariant models which are known to be universal, and this is a good example of one. Okay, so let me show you how you can encode message passing with equivariant networks. So for those of you who know about message passing, basically the core operation, I'm simplifying things a bit just for the kind of to streamline this presentation. So the core operation in message passing is that you have a graph, and each element of the graph has some information, like these colors. And what you want to do is you want each of these nodes to look at, receive information from its neighbors and aggregate them in some way, and then refresh its own color in some related way to the things it saw at its neighbors. So the core operation that you need to implement for message passing is to multiply the pair vertex feature vector with the adjacency matrix. Okay. So what I want to show you is that this operation, which is by the way equivariant, right? Because if you permute this thing and you permute this thing, then the permutation between the matrix and the vector cancels, and you get something which spits out the permutation. So this operation is equivariant by itself. I want to show that you can represent it as a composition of linear equivariant operators. Okay. Maybe it's not surprising that you can do it, but still it's not obvious that you can. So I'm going to show it. I know it might be a little bit confusing, but I just want to kind of give the essence that the fact that you can approximate this thing with linear concatenation, composition of linear equivariant transformations and nonlinearity. So the first thing that you want to do is maybe take this vector and put it on the diagonal. This is an equivariant operator. Permuting the entries will permute the rows and columns of this diagonal matrix in the same way. And then we're going to broadcast each of these colors to its column. Okay. Again, this operator is linear and equivariant. If you permute linear, it's easy to see because we just plug in here entries from here, like we copy this number here from here and so on. And it's equivariant because permuting the rows and columns would permute also here the rows and columns. Okay, the columns are constant, so in that sense it's clear. And then we're going to do an MLP on the feature dimension. You can always do that. That's always equivariant. It's also, like I mentioned, that any nonlinear operator which is entry-wise is equivariant. This is something like, this is the identity function in this equivariant space. So you can multiply using an MLP that approximates the multiplication. You can multiply each entry here and each entry on the adjacency. So you get maybe something like this. And now you can sum the rows and put it again on the diagonal. This is again a linear equivalent operator. So anyway, maybe the actual mechanics of how I constructed it is not really important. The point being is that a message passing can be emulated with equivariant linear layers and nonlinearity like ReLU. Okay, now so we saw that equivariant networks can emulate message passing, but in fact you can prove something much stronger if you allow the inner variables in your network, which are again tensors, to have an order greater than 2 or arbitrary. Then you can basically have this model. This is the universal model. You can approximate any equivariant function to any permutation subgroup. Okay, so if you have, this goes beyond these data structures that I mentioned. It includes them, but goes beyond. If you have any symmetry, it can be complex as hell, any subgroup of Sn, and you have some function which is equivariant to this symmetry, you can approximate it with equivariant networks, where if you allow yourself to have high order tensors. Of course, high order tensors are not useful, not tractable. You cannot really have a 4th order tensor in the memory, and it's not very useful. But at least as a theoretical tool, it provide at least an example of universal model, which is not a trivial one. Okay, so let us go back to graphs and try to kind of see where we stand in this landscape of methods, and maybe try to come up with methods which are strictly better than the things that known before. So the first thing that we know is that so we want to basically have an axis here that on one side we have efficiency of models, basically small number of parameters and maybe low memory footprint would be here. And on the other hand, we're going to have models which are powerful in the sense that they can approximate hard graph function. Okay, I don't know, graph isomorphism, or maybe things even more difficult. So we already saw that if we don't restrict the maximal tensor degree in our model, we can approximate any function. Okay, so if you have a function that highlights the maximal click in a graph, you could approximate it if you allow your equivariant network to have unbounded, not like very large interior tensor orders. But in order to kind of classify wherever interesting things happen, where we actually go near the efficiency bar, then we have to put some axis here, right? We have to put some way to compare different models. So what we're going to do is we're going to use something that was suggested 1 or 2 years ago. We're going to actually take a class of algorithm from computer science that solves a hard problem, and we're going to use those as to benchmark the networks. So the actual choice that people did, which we actually liked and used as well, is this K-Weizmann algorithms. These are all polynomial algorithms. It's a hierarchy of algorithms, and each one in this hierarchy does a better and better job in separating non-isomorphic graphs. And the first one in this hierarchy is called color refinement. I'm going to show it really quickly. And then we're going to use this ladder of K-Weizmann, the 2, 3, 4, 5, 6, 7, as a way to place a neural network in terms of expressiveness, and this is going to give a way to compare the expressivity of graph neural networks, which is in dire need if you want to actually improve the ability of neural networks, except of trying it on data sets. So what is the first hierarchy in the Weizmann algorithm is color refinement. It works like this. I'm actually going to implement this algorithm. I'm going to apply it with you on this small graph. So the way it works, and there is a reason why I show this. I'll give a spoiler. It's really similar to message passing. Okay, so we start with this graph. We have the color blue at each vertex, and we have this connectivity here. And now the way it goes, the algorithm works as follows. Each vertex looks at its neighbors, okay, and construct a multiset, meaning a set with possible repetitions of the colors of its neighbors. And then it creates a pair where at the first entry in the pair, it encodes its own color. And in the second entry, it puts this multiset of neighbors. So for example, this entry is color blue. So the pair would be blue here. And it has one neighbor, also color blue. So there's a multiset with the blue here. Let's look at this one. This node here is color blue, and it has two neighbors, also color blue. So we have a pair blue and a set. So a set because we don't really know we don't have a canonical ordering to look at the neighbors. So we look at the set, and each one of them is blue. So I do it for all the vertices. And now what I'm going to do is I'm going to color the vertices based on these unique identifiers. So there is some hash function that for each of these tuples provide a unique color. So for example, pink is BBB and blue is BB, which is has a political context. And I don't know, maybe green is B and a triplet of Bs. Anyway, after I colored, I can forget the labels. And I continue this way until things do not change. Do not change, meaning that groups of same color vertices are not getting broken to smaller groups. This is a stationary point. Then I stop and I create. So okay, I don't want to continue this. This basically here, this is the final stage. And then what you do is you create a histogram of the colors. And then the test is as follows. If you have two graphs, you can compare the two histograms. And if you get different histograms, you can say that these graphs are not isomorphic. This is not true. I mean, what we are guaranteed to get is that every two isomorphic graphs are guaranteed to get the same histogram. Yeah, that is guaranteed. But if we have two non-isomorphic graphs, they can be actually united by this algorithm. Okay, so here I'm going to show you an example now. So we put here this ladder of the KWL. And if we think about this color refinement, this is the first algorithm. Here I'm showing you two graphs. These are non-isomorphic graphs. But this color refinement algorithm would provide the same histogram for those two. Okay. So basically, you can think about isomorphic graphs as those equivalence classes of graphs. And the 2WL would make these two equivalence classes in the same equivalence class. However, 3WL would separate these two. So it will break these two and provide different histograms. And every time you go with this ladder, you're going to have more and more complicated examples that separates between KWL and K plus 1WL. Okay, so this is, for example, a separation between 3WL and 4WL. Okay. All right, and so what we said so far is that the 2WL, so if you kind of pay attention to the definition of this color refined algorithm, it's really similar to message passing. And it turns out that if color refinement cannot distinguish between the two graphs, for example, these two cases, then message passing cannot learn any function that distinguishes between these two graphs. Okay, so message passing will always spit the exact same result for these two graphs. Meaning, for example, that message passing cannot learn the number of connected components in a graph, right? Why? Because it will always fail on this case. By the way, the reason it fails here is because these are regular graphs. All the degrees are the same. So unless you provide some feature vectors on the nodes that are going to help him, message passing will never be able to separate these two graphs, okay? the two equivariant networks that are presented are also in this class. They cannot separate these two graphs. However, one thing that we proved is that if you take a k equivariant network, so you allow your order of equivariant network to rise until the level of k, then you will be able to emulate KWL. So you'll be at least as good as KWL. So if you want to achieve, for example, 3WL, which is strictly better than message passing, all you need to do is do equivariant networks where you allow the middle layers to have a 3-order tensor. And then you are guaranteed to have something which can separate these two graphs. However, having a 3rd-order tensor in memory is not something which is very useful. For things which are not small graphs, this is actually not very practical. So the last thing I want to show in this context of graphs is a way to create a 3WL algorithm for learning graphs. I mean, a graph neural network which has the power of distinguishing a non-isomorphic graph as 3WL, but does not hold the 3-order tensors, but work only with matrices. And the idea here is that you can actually replace the high-order tensors with high-order polynomials. So far, we only discussed linear equivariant layers, but you can think about other layers, like maybe quadratic equivariant layers. One extremely useful quadratic equivariant layer between matrices is matrix multiplication. Okay, maybe the most famous operation of them all. So if you think about two matrices and you multiply them in regular matrix multiplication, then this would be a quadratic operation, of course, in the entries of the matrices, but it also will be equivariant, because if you conjugate this with a permutation, the right matrix, and you conjugate the left with a permutation, then the permutation in the middle would cancel and you get conjugation of the result. So this is also equivariant operation. It turns out that if you add this operation to your basis, you can actually achieve higher expressiveness than just 2WL. You can achieve 3WL. Okay, so let me just kind of give you the bottom line of this observation. So you can construct an extremely simple graph neural network, which is equivariant, so it's well defined, and it's equivalent to 3WL, so it's strictly better than message passing. And all you have to do is to use blocks of this format. So you have the input to each layer is like a matrix. Again, there's a feature dimension which I'm ignoring here. And now you perform an MLP to each of the input. The MLP is only in the feature dimension. And then you do matrix multiplication of matching layers, and you concatenate the input. So this is actually a PyTorch implementation. That's the entire implementation. It's not a pseudocode. So you do MLP, matmul, each feature dimension is matmul, and then concatenation. This is the entire code. Turns out that this extremely simple network is strictly better than message passing in terms of expressiveness. The downside of this network, by the way, is that you need to keep those dense matrices in memory. Okay, so message passing only keeps a sparse adjacency and a vector of values on the nodes. This actually keeps it's like a full graph. But the benefit is that it can learn much more complicated function than message passing. This is like a benchmark on a standard graph neural networks. Can't say that we beat everything. I think the method ended up in the top 3 in most of the cases, but not always. To be honest, each of the method that uses the data set uses a different settings, so it's like splits are different, so it's really hard to compare, but in general it seems to doing pretty well on this standard examination. Okay, I want to use like the 5 or so minutes I have left to talk about the other part, so it's not really half-half, about implicit neural representations. So I'll use 5 minutes or so, and then maybe we can talk if you have some questions or whatever. So the implicit neural representation is an interesting way to use neural networks to learn geometric data. In the left-hand side is maybe the classical way we use the neural network for classification. So we have an examples of, let's say, minuses and pluses. And what we do is we train neural network using some loss. And then the red line here, which is the zero level set of the network, also called the decision boundary, separates the positive and negative examples. An interesting way to think about neural network is instead of giving it a positive and negative examples, you can prescribe only examples that are positive, okay? So maybe lies on some low dimension manifold or something like that. And then what you want your network to do is to be zero on those points and change sign between, okay? Changing sign would guarantee that there is a manifold created here, which is of lower dimension 1 and passes through the points. So we call this right-hand side implicit neural representation, because these are implicit representations of things which are defined as a zero-level set of a neural network. One way you can, for example, one test case you can use it with is if you have a point clouds in 3D. So you have a bunch of like this, a bunch of points floating around. What you want to do, you want to find an implicit neural network where the zero-level set passes through the points. So there's a lot of work that's been done in this context. The main point is that people either use grids or predefined bases, that's the pre-deep learning era, to find those functions. Or if they use deep learning, they either use convolutional neural networks and they find this function on a volumetric grid. Or one example which is related to what we've done is to use neural networks as the implicit function. However, the way that people train it is by regression. You have a supervision. So you start with an implicit function that you have samples of, and you just train a regression loss for this implicit network to be as close as possible to the ground truth implicit function or the pre-computed implicit function. An interesting question is whether we can use implicit neural network to learn the surface by itself without prescribing the complete answer of the implicit representation everywhere. So I'm going to show you quickly two things. Two different approaches to it. Here's the first approach, which is extremely simple. So you can think about the loss of the following way. So this is you can think about regression loss. So tau is some sort of a regression loss. This is like integral over x. Hx is the input. It's an unsigned distance function to the point cloud. For example, you can think about this, which is like the L2 distance to those white points, or maybe this, even the indicator function. So 0 on the white points and 1 everywhere else. Both of those are relevant input. And basically you want to find a neural network F, which is as close as possible to this unsigned distance. Unsigned distance is it's not like the signed distance. It's something which basically is readily available. And now you can do the following thing. You can start with regression. Sorry. You can start with regression. So regression would mean, for example, that we just subtract f and h and take the absolute value. If you do that, you're going to end up exactly with the function h of x as input. Okay, so nothing is achieved here. But what happens if you do the following thing? Instead of standard regression, you put an absolute value on the first term. So we call this unsigned similarity or regression. It turns out that if you do that, you introduce new local minima to this function now. Okay. In order to understand that, look at this image. So think about the unsigned distance. This is a one-dimensional illustration. You have one point, and you have this black line, this unsigned distance to this black point. It's shown here as a function over the x-axis. And let's assume that the network looks like this as the current stage. So actually the unsigned similarity would measure the difference to the unsigned distance up to a sign. So it basically will try to minimize this yellow area captured between the curves here. Now, if you do gradient descent, you can imagine that it will converge to the signed version of this function. And indeed, if you do it in practice, you get things like that. It turns out that the network, when you answer this unsigned distance function, you get this, where the black is the zero level set. So it's actually changed the sign and interpret the point in an interesting way. Okay, that's the first thing. I'm gonna jump on this for a second, and I want to show you the second thing. I'm gonna finish after that. So that's my last. It's not my last slide, but point. So another way to tackle the same problem is using something that is called iconal differential equation. So let me quickly show you that. So when you think about iconal, so what is iconal equation? It's a nonlinear partial differential equations, and it works like this. It has a boundary conditions. For example, think that you want a function that is 0 on this L-shaped boundary, this black boundary. So you ask it to be 0 on this set, and you ask the gradient of f to be of norm 1 everywhere else. Okay? It turns out that if you solve this PDE, it has some issues in terms of what type of solution exists, but let's forget that for now. If you solve that PDE, it turns out that you get the sign distance function to this curve. So you actually get the distance to the curve multiplied by a sign, which is, for example, +1 at the outside and -1 in the inside. Okay, so that's the iconal PDE. Now, the question is what happens if you break the rules and provide something which is not well defined for this PDE. So instead of providing a really nice boundary of some domain, you prescribe a bunch of points like this. So now you think about the punctured, so the punctured plane, so the boundary would be just these points. The problem is that the PDE is not well defined in the sense that, for example, these two solutions are both equally good solutions to the PDE. Both of them have 0 that goes through the boundary and gradient 1 everywhere, because both of them are a sine distance function to some curve that goes through those points. Okay, so the next thing that you can do is put this thing as a loss. So let's assume that we write a loss where we want f to be 0 on the points and the gradient of the network to be 1 everywhere. Everywhere we do it by expectation. So when you minimize this, and now I'm taking a standard MLP, nothing special, and I minimize this on this bunch of white points, it turns out that the result is this one, okay? So somehow the network chooses to pass a straight line to these points. There's no prior here. It's just 0 on the points and gradient 1 everywhere. In fact, it actually performs really interestingly. If you take points on a unit sphere, so you take these white points and you minimize this creature, you're going to get this result. So the network somehow provided, if you want, a smooth explanation to the points, a minimal curvature in a sense. And even if you random points, like the example on the right, the networks provide a really nice interpretation of those points. So it turns out that we call this an implicit geometric regularization. So it's kind of a geometric kind of appearance of this implicit regularization that happens in networks, and you can really see it in practice. So the network somehow favors smooth solutions to those iconal equations, although nothing like that is restricted. We feel this is really connected to this body of work on implicit regularization. We try to think about it, but there's a lot of other things to do. Let me finish by showing you maybe one result. I'll finish with, so it turns out that it works really well. Here's like, I'm going to finish with this. This is actually a way to represent, you take a bunch of images and you use this implicit regularization to reconstruct geometry and illumination using this method. There are some other details, of course, that I'm not telling you. But anyway, what you're seeing on the left here is a neural network learning three-dimensional model, including, by the way, illumination and a little bit of BRDF, completely unsupervised from the input images on the right. That's it. I'm done. Sorry for taking the whole hour, but anyway, if you have any questions, I'm happy to talk.
Okay, this form factor is kind of difficult for clapping, but so we're a little bit out of time, but I think let's just take one more question, and I guess other questions would need to be offline. Okay, so does anyone have a question?
I can ask?
Yeah, go ahead.
You mentioned the Bell number being independent of the number of vertices. I couldn't quite understand this because I thought the Bell number is the Bell number of the number of vertices.
No, it's the bell. Okay, so let me. So I guess this is just related to what is bell number of what. So the bell number is not of the number of vertices, but the order of the tensors. Oh, okay, wait. Sorry. There's a momentum to slide. Let me do like this. Okay, so can you see it? So the bell number is not of the number of vertices, but the order of the tensor. So if you have like a matrix is n by n. So it would be 2. And if the output is a matrix, it's again going to be 2. So the bell number is bell number of 4. Just 4. It's not related to n. So,
okay, thank you.
Okay, so let's thank our speaker again. And yeah, I guess we'll need to take other questions offline.
Thank you, and sorry for taking all the time.
Okay, so this concludes our meeting. Goodbye.